Okay, so this is lecture number 29 of EE 503, and today we are starting the topics of estimation. Okay, so up to now we have discussed signal modeling, stochastic modeling, random processes, etc. And 2/3 of this course is almost over. Okay, I think we are left with lecture 29, 1/3 of the course, and for the rest of the course we will be discussing estimation topics. Actually, this is the processing part of statistical signal processing course. Okay, please remember that our course title is Statistical Signal Processing and Modeling. So we are done with the modeling aspects. So what do I mean by estimation? Now let's consider a problem like this. Very generic problem. So I have theta 1, theta 2, theta 3 as, let's say, these are desired variable, meaning theta, possible values, or let me write it better, possible values for desired variable. For desired variable theta. So let's say that you are trying to estimate the position of a car. Okay, so the car can be x meters away, y meters away, z meters away, and so on. Okay, so you have list of possible values, but maybe this is there is a restriction. Maybe these quantities are always positive, they're always negative, they are some discrete value, and so on. So we have a, let's say, a list of possible values for the desired variable theta. So what we observe is not these variables, but maybe a mapping of these variables. Okay, so this is observation number 1, observation number 2, observation number 3, let's say observation number 4. So there is a mapping like this. I'm just making this up. Okay, so what do I mean by this mapping? Well, most of the mathematical objects, they almost always have such mappings. Okay, but what is different with this time is, now, for example, theta 2 is mapped to possible two, let's say, observations. Theta 2 is mapped to either O1, observation number 1, or observation number 2. So in a mathematics course, let's say in a basic mathematics course, we have similar mappings, please remember. For example, we say this is f of x, isn't it? So every x is mapped to a possible y location. Let's say x1 is mapped to y1. Okay, but over here theta is mapped to two possible quantities. So how can this be possible? Well, with this mapping we are assigning some probabilities. Let's say that this is 1/3 probability, this is 2/3 probability, and so on. As you see, this becomes a probabilistic mapping. So theta 3, let's say that this is 1/5, or let me have 1/6, because I have 3/6 and 2/6. Okay, and this one is, it's only mapped to this, so this for certainty with probability 1. Okay, now the question is, I'm only observing this part. This is my observation. And of course, what am I trying to do? I want to do a reverse mapping. For example, I have observed O3, observation number 3. So what is theta? Okay, this is the estimation problem. Actually, this is the fundamental problem of almost every mathematics problem. For example, I have observed y1. So what is the x value? You say x1. Okay, because there is only one y1. This is the inverse function. This. But what happens if I observe, for example, this quantity? Let's say y2 over here. Now, this function is not invertible because for y2, what we see is that I have three possible you know, x values, all of which, let's say xa, xb, xc. Okay, xa, xb, xc. They're all mapped to y2. Okay. So in the calculus problems, we say that this is not an invertible function and do not discuss the inverse operation. F of x is not an invertible function and do not discuss the, you know, its inverse and so on. But we may in practice face with such situations. You observe something, but this observation can be resulting from theta 3 or theta 2. Now your task is, you know, how you decide, you know, which one is, whether theta 2 or theta 3 is, how should I say, is a better choice for theta, given the observations. Okay, so this is a task of estimation, and so from observations, the reverse mapping, you may say, from observations to the desired variable theta. So let me discuss it a little bit further. Now, classes of estimation problems. We are interested in this course in only one class, but to understand that class, you have to be aware of other classes. So I may say that, let's say that this is the topic of estimation. This is divided into two. So what we call non-random parameter estimation is the first topic. And the second one is, let me see, this is called random parameter estimation. Okay. So what do I mean by that? Over here, while this theta variable, this desired variable, theta is non-random. Over the other one, in the other one, theta is a random variable. Okay, theta is a random variable. So, what is the difference? Well, it makes a lot of difference because in one of the cases, you have a prior information. For example, you have probability of theta 1 is equal to some number, let's say P1. In the other one, probability of theta 2 is P2. For this one, probability of theta 3 is, let's say, P3. Okay? So this one, random parameter estimation, assumes that, let me write it, i.e. assumes a prior distribution. Prior means before the experiment, before the observation, before we receive the observation, let's say. I.e., this one assumes a prior distribution for theta random variable. Okay? Actually, this is something great because, for example, if this is like 99% and this is like 0.005 and this is 0.005, then without any observations, I can say that, well, theta 2 is the result of this experiment, okay? Because this is correct 99% of the time. So 99% of the time, this mapping starts from theta 2 and goes somewhere. 99% of the time. So even not looking at this observation, now it makes sense to say that, well, theta 2 is theta 2 is the desired variable because this experiment starts with theta 2 99% of the time. So this is the a priori distribution, okay? Or a priori information about this theta. So once you receive this observation, you can update your a priori distribution or a priori observation to the posterior observation. So the goal is, in general, to get the posterior distribution. The posterior distribution. So what is that posterior distribution? So I have this theta random variable. So this is prior, and Now, theta given x, let's say. Not x, let's say observations. Okay, theta given, let me write observations. So conditional density of theta given the observations, given this outcome of this mapping. This is called posterior. So in general, we would like to calculate, we will see why we end up with such a statement. This is called the posterior probability, and we are very much interested in this posterior distribution. Okay. So when we come to this one, well, non-random parameter estimation, we have no ideas about these probabilities, let's say. Okay. Maybe this is the very first time that we are making this experiment, and we are thinking that all of these are, some possible values, but I cannot say anything about which one is more likely at the beginning of the experiment than the other one. So I have no prior information. Okay. So non-random parameter, no prior, I think prior is this, it's clear. No prior information. And for non-random parameter estimation, the basic tool is what we will see immediately. This is by maximum likelihood. So what is this maximum likelihood? Well, maximum likelihood is this. Let me write this likelihood first. So now I have this observation, okay, one of these, not given, but given theta. So this is what we call likelihood. Let me write it with given notation, because as we have seen, theta can be random. So if theta is random, there is a distribution associated with that. If theta is not random, now you may say that this is deterministic, or its distribution is just an impulse. Okay, impulse at that location with probability 1. Okay, so this is what we call likelihood. So what is maximum likelihood? Let me write it over here. So theta maximum likelihood estimate is argument maximizing. I will explain this immediately in more detail with an example of this theta. Okay, so we are maximizing over this. For example, your observation is observation number, let's say 1. Okay, so if this is your observation, now you do the following. This observation can result from theta 1, theta 2, theta 3, but theta 3 is not mapped to that. So it may result from theta 1 and theta 2. So I have no idea about which one is more, likely at the beginning of this experiment. Then I compare only these blue values, 1 and 2 over 3. Then I say that 1 is greater than 2 over 3. Then I say that observation 1 is, so its maximum likelihood estimate is theta 1. It's as simple as this. Okay. So let's look at this. Observation given theta. Okay, observation given theta. So this is, for example, this is our observation. If I condition this observation with theta 1, what is probability? Observation is O1 given theta 1. Observation is O1 given theta 1. Well, this probability is, that probability is 1. Observation is O1 given theta 2. That is this transition probability, 2 over 3. Observation is 1 given theta 3, or O1 given theta 3. Okay, so I'm trying all possible thetas, as you see, and I'm trying to maximize this function. Okay, so what is that function? Let's look at this one. Maybe this is more richer. Okay, observation is 2. So observation 2, given that I am over here, so this is that statement actually. If you are at theta 3, then you reach observation 2 with 2 over 6 probability. Okay? So indeed these transition probabilities is this probability. So for the maximum likelihood, I'm maximizing over, let's say, this probability is in this, you may say, channel. Okay? Input is, inserted into this probabilistic mapping, and what we see at the output is these observations. So this is the channel, transition channel. So this is the mapping probability or transition probabilities. So I'm discussing, these transition probabilities, okay? And I'm maximizing them given the observation. So observation is obviously fixed. This is my observation, O1, O2, O3, and I'm trying to set a theta for that. For example, if your observation is this, your estimate is theta 1. If your observation is this one, now these two are equally likely. You flip a coin, doesn't matter, there is nothing else to do. You say either theta 2 or theta 3, but not theta 1, because it has probability, it has likelihood 0, okay? How about for this one, observation number 3? Observation number 3 can only, it's only mapped with this. All other possible, they always have 0 likelihood. This one, it's always, because observation 4 is only mapped with this. So as you can feel, this makes some sense. This likelihood operation likelihood interpretation and its maximization makes some sense in this estimation problem. But, well, this maximum likelihood, this is an approach. Let me write with the proper color. This has no optimality guarantees. You may be surprised it's looking like a reasonable thing to do, but it has no optimality guarantees. What does it mean? There can be some other estimators which has smaller error variance, let's say, okay? But even though it doesn't have a strong optimality property, we will discuss some of its properties immediately. It's being widely used and it's very applicable in many applications. It remains applicable. Okay, so let's go on with our discussion. So I'm going with this, even though my focus is the other one, just to understand this. So non-random parameter estimation. Okay, so I will discuss this with an example. So let's say that x of n is c plus w of n. Okay, c is non-random parameter. W of n is, well, IID and 0. Is it 0? Okay, sigma n square. I have this. Okay, so x of n for n is equal to 1 to capital N is provided as observations, okay, because I have plural, I have n, capital N observations. So what's going on? So c is a constant. I don't know its value. It's a real number, so it can be any real number. So let's say that this real number is this. So this, let's say it's a real line. So this is mapped to some other real numbers by, this is unknown, let's say theta 2, by adding Gaussian distribution, so I get another real number. Okay. Now the question is, these observations are right now a vector, because I have n of those observations. Now the question is, find maximum likelihood estimate of C. Okay. So how can I think about this problem? Maybe you are measuring something, a constant value. Maybe you are measuring the resistance of a resistor. Okay, this is your multimeter, and you have n of those measurements. But those measurements are different from each other because of this noise effect. But you know that multimeter operates with such a statistical behavior, meaning that its noise is zero mean, and its variance is sigma n square. Okay, this is how multimeter operates. Okay, there is some noise in the multimeter output, let's say. Now the question is, what is the resistance? Okay, given I have n of these, I can say that my resistance is my first measurement or second measurement, or I can say that it is the average of them, or I can say that it's the average of first and the last measurement. So how can I find a good estimate or a reasonable estimate for C? That is our problem. Okay. So we will apply this maximum likelihood principle. Okay. Now in this problem, let's say solution. Now I can write this density as x1. So these are the observations, xn, given, let's say. But since over here C is, let me use this notation, just because it says something else in addition to this. Now I'm assuming that with this notation, the right-hand side of semicolon contains non-random quantities. Non-random, let's say, variables. So with this notation, I can also tell the reader, let's say, okay, or some other person we are communicating, that this C is non-random. So actually I'm talking about this distribution of joint distribution of n observations, where C is just a parameter, non-random parameter of that observation. Okay. So since these are all IID, so I have nothing but K1 to n f xk C. Am I right? Because they are all independent. C is just a constant. Okay. So what is this one? Now I can write this distribution 1 to n 1 over 2 pi sigma n. Let me write it a little bigger. 2 pi sigma n square e to the minus, this is, well, I have switched to this notation, xn for this, okay, because to save space, xk minus c parentheses square divided by sigma n square. Because kth observation is nothing but Gaussian distribution with mean c and variance this one. So this is this, kth observations density, Gaussian distribution, and so on. So what should I do? I should maximize, let me write this, C maximum likelihood estimate as argument maximizing, let me write this as density as in vector form over C, okay, arg max. So this is, one more time, I define this as my vector x1 xn, because we are used to working with vectors right now. Okay, so please note that I can also write this as arg max over C log, well, there is only one term, so f x this. So this is called, as we have said, likelihood, and we are maximizing likelihood. This is called log likelihood. So I am looking for the optimal x value, maximizing the likelihood. But since logarithm function is a monotonic function, monotonic increasing function, if I have a c maximizing this one, it's also maximizing its logarithm also, okay? Because logarithm is a monotonically increasing function. Okay. These are all positive arguments, as you see, okay? Because these are all probability density functions. They are, greater than equal to 0, and so on. Okay. So I would like to maximize the log likelihood function. So logarithm is well defined in this. So I can do my operations. Okay, so what should I do? Well, let me take the logarithm of this. If I take the logarithm of this, log of this, so what do I see? So, well, okay, C minus I see this. So what, oh sorry, this is, let me call this a constant. Because this C and this C may confuse us significantly. Okay. So if I take the logarithm of this term only, I get log of this plus log of this e to the something, but that is just minus something, this thing, exponent. Okay. So since I have n of these, I am adding those, this is a product, then in the logarithm you are summing all of these terms in the product. So this is like, I have the same constant appearing n times, and this is the summation of the exponent. Again, summation contains n terms. Okay. So as you see, this is the reason that I would like to introduce log likelihood, because, you know, as you see, if once I take the logarithm of this, this becomes a rather easy problem to maximize, is a maximization problem. So what should I do? Now let me take the, let me call this JC, okay, a cost function. So my goal is, let me write it over here. Let me, before introducing, okay, let me introduce this as JC, or let me do this way. Let me introduce this part as JC. Okay, so my problem becomes arc max C JC, but there is a minus sign over here still. Okay, this is that minus. So this constant, of course, it does not affect this maximization because it's not a function of C. I'm looking at, I'm not interested in the value of this maxima, but I'm looking at where this maxima is happening. That is, I'm looking at the location of this maximum. Okay. I'm trying to find the value of C, maximizing this function. Okay, so this minus sign is over here, and clearly I can say that this is arc min JC, because if you are maximizing this minus JC at a C, then you are minimizing this part at the same C value. So at the end, this is the problem that I'm interested in, then the optimal C value will be my maximum likelihood estimate. Okay. Now let me try to solve this. Then take the derivative of JC and equate it to 0. Okay. So if I take the derivative of this, this is equal to this one. Well, I think it will be clear in the next step. Divided by 2 sigma n square equated to 0. So I have summation 2 xk minus c. There is a minus sign also, divided by 2 sigma n square is equal to 0. So if I take the derivative with respect to c, 2 comes as a factor. There's a minus sign because of minus c over here, and so on. But these terms do not affect anything because they are cancelled by the 0. Okay. Now what do I have? Then the solution of this becomes, so this is k1 to n. N times c is equal to summation of 1 and xk. Okay, separate the c. Now this constant is added up n times, so I have n times c on this side. Then I have, let's get rid of this 2 also, summation of this x case. Then this is my final result. The maximum likelihood estimate is 1 over n over n. Okay, so this is the maximum likelihood estimate. Okay, this is also called in signal processing, let me write it over here, sample mean. This is very famous. Now you have n observations, their average value is called sample mean, or its maximum likelihood estimate for this model, for the Gaussian model, IID Gaussian model with, you know, constant variance, noise variance. Okay, so this is about maximum likelihood estimation, as you see, what we do. Now I want to discuss the properties of estimators. Let me erase this part also. Properties of estimators. Number one, bias. An estimator is called unbiased if expected value of theta is equal to, expected value of theta hat is equal to expected value of theta. Okay. So what is this expected value of theta hat? Well, let me have this then. Okay, this can be even a vector. Okay, so this is theta hat x is the estimator for theta, estimator for theta, where x is observations, observation, let's say vector, like in this case, x case. Then theta hat function is this averaging function in this case. So this is the expected value of this. Okay. So in this example, C is non-random. Okay, let me connect with this. So this is the definition. It's called unbiased if this is equal to this. Okay. I have this. So in the previous example, let's say maximum likelihood example, C is non-random, then expected value of theta hat x, or let me write C hat of x is equal to C, should be equal to C for an unbiased estimator. Okay. So now is this C hat? Let's check whether this C hat is unbiased or not. It's an unbiased estimator or not. Whether, let's check the sample mean is an unbiased estimator or not. Well, what should I do? I should only evaluate this expectation and then compare it with the right hand side. That is it. Okay. So let me erase this. I think it's clear. This is let's keep the sample mean over here. Okay. Then if we go this way, then expected value of this is equal to, this is my maximum likelihood estimate, expected value of summation of xk divided by n, k1 to n, I have this. And this is equal to, well, expected value of xk is, xk, let's remember, this is C plus noise, wk. C plus noise. Noise is zero mean. C is constant. So this is C, as you see. Okay? Because this is nothing but, expectation of this one is equal to 0. So I have C times n divided by n. So I get C. So since I have this part as C, okay, we see that sample mean is an unbiased estimator. Okay, so this bias issue is very important in estimators. Okay, this is one of the first important issues. For example, let's say that we are interested in this theta, and true value of the theta is this. We have some observations. Now, if this observation gives us, let's say, theta hat for the first observation vector. Now, it gives us another example or another, let's say, experiment. I have a second set of observations. I run the same estimator. I get over here. So you see that this red colored markings are our estimate values. So what do you see? Well, if you see that, you know, in such a case, you can say that the average of these red values, their mean value. So I'm talking about this ensemble average. If it is a true value, then you say that on the average, my estimation results match this true value. Okay? Sometimes maybe it can be, you know, exactly on top of this true value, but on the average, I say that it's always like that. So this is the case when this estimates expected value of the estimator results, the red dots, after this averaging operation matches this true value. Okay? This is for the maximum likelihood case, like this one. If this quantity is random, then it should match the mean value of that, if this is a random variable, if theta is a random variable. So in some cases, you know, you may have a situation like this. Now your estimates are skewed to the right. Okay? So this is no good in the sense that their average behavior is around this point. Let me say that this is expected value of theta x over x observations. Now this becomes, you know, the difference between those two becomes the bias. Okay? So this is the bias of the estimator. So for example, assume that, you know, assume that you are a hunter. Okay, you want to hunt this, but you are aiming your rifle towards right all the time, so you never hit this value. Okay, so you miss it by this amount. Okay, so as you can imagine, this bias is a very important problem. Because of this bias, you may be making, you know, the same kind of, you know, this kind of mistake, the displacement of the true value and the estimates value again and again. Okay, so you should be aware of this bias calculation. So in some problems, bias can be, in some problems, not all, a fixed quantity, meaning that it is independent of, well, independent of, let's say, theta. You know, this theta true value of this, independent of theta true. Then you can subtract bias from your estimates. Essentially, you create another estimator, i.e., you generate a new estimator, theta, let's say 2 of x is equal to theta 1 of x minus bias. Let's say minus of bias of theta 1 hat. Okay? Then obviously this is unbiased. Then the new estimates are unbiased. But of course, in general, you are not that lucky. You cannot easily subtract that, but in some problems this may occur. So the important conclusion is be aware of this bias. If there is some bias in the system, then you are in trouble in many cases. Okay, so this is the first property. Now there is another one. So sample mean turns out to be unbiased. Good news. We don't have to do anything. Number 2, this is consistency. Okay. So consistency is an estimator is consistent. So this is the definition. If expected value of theta minus theta hat parentheses square goes to 0, okay, as the number of observations that is n in our case, or dimension of this vector n goes to infinity. Okay, n goes to infinity. So let me not use these black markers and use the others. Okay. So this is an n by 1 vector, like in our earlier case of sample mean. So now you see that what happens if I increase number of observations to infinity? Do I get, 0? So what is this? This is the error. So this is, you may say this, if it is unbiased, 0 mean. If the error is if error is 0 mean, let's say, this is unbiased case, then this is the error variance. If the error variance is approaching 0, as n goes to infinity, we call that estimator consistent estimator. So let's check. Let's check consistency of sample mean case, sample mean example. Okay, so let me define this error. Theta minus this in this example corresponds to, so this is my error, estimation error. So this is C minus this thing. Oh, sorry, this is divided by n. C minus this. This is my estimation error. Okay. Well, I should take square of this and minimize it. I mean, not minimize. I should take the square of this and evaluate the expectation. Okay. So C minus so I want to evaluate this. So previously, when this error, estimation error, has 0 mean, what does it mean? Expected value of theta is equal to the expected value of theta hat. This is, this unbiasedness condition. Okay? So if this estimation error has 0 mean, okay, take the expectation of this. Expected value of theta is equal to the expected value of theta hat. And this is nothing but unbiasedness condition. Expected value of theta, expected value of theta hat, and this is our unbiased estimator condition. Okay? So if the estimation error is 0 mean, we say that that estimator is unbiased. Then this becomes the error variance, as I have said. So how should I calculate this? Now, this is an expectation over x vector, all elements of x1 up to xn. But I have some difficulties over here. Again, I will be using, the fundamental property of expectation. This is C plus WK, isn't it? So if I insert that, C is constant. Then I'm taking expectations over W1, W2, Wn, C minus C plus WK over n. Okay? So this is a big result, because instead of taking expectations over one random variable, I'm taking expectations over another random variable. Okay? So this is the main feature of, you may say, expectations. Let's see then. So if I do this calculation, well, I get the following. Let me write this as W vector. Okay. Then I have C times N minus C times N. So there is also a square over here. Okay, let me put this square like this. So C times N's cancel. So I have something like this. There's a minus sign over here. K1 to N WK. Okay. Well, this is N square. Expected value of, I think it's clear, I guess, from this step on. Summation of expected value of WK square. Okay. So this minus sign does not do anything after taking a square. Okay. So I have N square on the denominator. So numerator square is, I have W1 square, W2 square, and cross terms. But since this is zero mean, okay, all of those cross terms and IID, zero mean and IID, all of those cross terms are equal to 0, so I get this. So that is it. So since again this is because of this, my final result is sigma n squared over n. Okay. So I have managed to calculate this. So I see that. So expected value of theta minus theta hat, which is equal to sigma n squared over n, parentheses square, goes to 0 as n goes to infinity. Okay, so this is the result. So we see that sample mean is a consistent estimator. Okay, which is very good. So we see that the sample mean also satisfies this consistency. So consistency is a very important property, because you see that if I collect more and more information, I get better and better estimates. For example, like for sample mean estimator, well, let's remember, C, maximum likelihood of access, nothing but this. So what is the distribution of this maximum likelihood estimate? Well, this is N, C, sigma n square. Okay? So this is distributed according to N, C, sigma n square divided by N. Okay? So how can I write this, in such a way? Well, the reason is, what is the mean of this? This will be a Gaussian distribution at the end. So what's the mean of this? The mean of this we have calculated, because it's unbiased. It is C. So what is the variance of this? The variance of this one is, forget about the mean for the variance calculation. So since, again, exactly this calculation, you see that it is the variance of the numerator is n times sigma n square, and on the denominator I have 1 over n, I have factor 1 over n, so the same calculation happens, so I get this. So what do I see? I see the following. If this is C true value, let's say, okay, let's see, we have used C. Now you have a Gaussian distribution like this, and this Gaussian distribution has always mean around C, but it's getting, let me use this. Okay. Let me use this. Okay. So what is this axis? So this is my C axis. Let's say that this is the true value. Let's say this is the true value. Okay. This is my estimate. C hat maximum likelihood estimate, and this is its density. Okay. So this is F C maximum likelihood, C maximum likelihood. This is the density of it. So what I see it, the following, for example, the green one maybe is for n is equal to 1000. I don't know. The red one is for n is equal to 100, and blue one is for n is equal to, let's say, 10. Okay. So you see that if I have only 10 observations, I see a distribution like that. So it's this distribution with n is equal to 10, Gaussian distribution. The mean value is a true value, but my estimate may be somewhere in here, okay, under this, large probability value of this blue curve. So if I increase number of observations to 100, you see that these estimates are converging somehow towards this true value. So with a very large probability in comparison to the blue one, I am around this close neighborhood of, small neighborhood of C true. For 1000 case, it's even very, narrow interval, including the C true. Okay. So this is, unbiasedness cases. The mean value of this estimate matching the true value. Consistency is the variance of this estimate goes to 0, as you see, as n goes to infinity. That is the consistency. Okay, now we have 1, 2, I think the third one is efficiency. An estimator is said to be efficient, or this is called sometimes statistically efficient. Statistically efficient if it's, let's say, if it is MSE, okay, let me write, okay, if it is unbiased and it's MSE, it's error variance, let's say, it's error variance, matches is equal to what we call equal to the Kramer-Rao bound. Okay. So what is this Kramer-Rao bound? So let me actually this is our MSE. Okay. Mean square error. So this is the desired quantity. So this is error square, and this is mean of error square, as you see. So this is called mean square error, MSE, mean square error. We will describe that mean square error in much more detail later on. So the result is this. So I have a lower bound. This is called Kramer-Rao bound. Okay. Of this is a function of theta. Okay, Kramer-Rao bound of theta. So this is, let me write this. Let me write it over here, CRB, Kramer-Rao bound. Okay. So some estimators have this. Previously we have calculated this error variance like this. So some estimators, MSE, this quantity matches the Kramer-Rao bound, and that's called an efficient estimator. Okay. So what is it? What is the importance of that? Because this Kramer-Rao bound is a lower bound for all estimators. So meaning that you cannot be operating with a smaller error than MSE. Sorry, with a you cannot operate with an MSE smaller than Kramer-Rao lower bound. Okay. So the smallest possible MSE is the bound, Kramer-Rao bound. Okay. So what is that one, Kramer-Rao bound? So CRB of theta. So this is, well, I'm briefly explaining this. Now we are taking the expectation over, well, this is x, sorry, d theta ln, this is this theta. Okay, so we have some other courses, 5506 course. This is the following course to this one. So in that course, this is discussed in detail, but I just want to mention this because we are discussing the properties of the estimators. So you can say that this is log likelihood. So Kramer-Rao bound is this calculation. Log likelihood is differentiated with respect to this non-random quantity. You take its square and take the expected value. Well, this is a little surprising. And Kramer-Rao bound says that, as I have said, this is a lower bound than all estimators that you can think of operate at a higher MSE than this Kramer-Rao bound. Okay? There are some details about this unbiasedness and so on, but this is essentially the picture. So let's see. Let's check efficiency of sample mean estimator. Okay. So I should calculate this. So this is ln or log. Log. This is this. So do you remember we have calculated this one as, I have written this one as constant, and there was this minus sign. Let me see. K1 to n. This was xk to sigma n square. Okay. So this is, I have something like this. So let me check this. Log likelihood. So for k is equal to 1, I have e to the minus this. I think it's correct. Okay. So again, I take the derivative of this. This is not the partial derivative because I have a single variable, as you see. Okay. If I take the derivative with respect to, sorry, I made a mistake at this point, xk minus c, because this is not zero mean. I have something like that. So this is, my desired quantity is c. So I'm taking derivative with respect to c. So I get, well, 2 minus 2, there is 2 sigma n square times xk minus c, k1 to n. Okay, I get this. Now I have calculated this one, this part. So this is, let me call this, okay, let me write this ddc log f okay, I have this. Now I should take the square of this, okay, and then evaluate the expectation. Wow. So if I take the square of this, I have, but let me write it over here. So CRB calculations continue. So I would like to calculate expected value of x, this thing, dc log x square. Okay. I have sigma n to the power 4 because of the square of this. Now I have this expected value of summation xk minus c xk minus c parentheses square over, this is the x vector. So I should take the square of this. Okay. Okay, xk minus c parentheses square. This is sigma n to the power 4. But again, this is an expectation over x, but this is nothing but w of k. So this is expectation over w vector, summation k1 to n wk parentheses square sigma n to the power 4. Okay, because as we have done, xk is nothing but, you know, a Gaussian random variable with mean c and variance sigma w square. Okay, then you subtract the mean, then you are left with noise. That is it. Now over here, now I have n times sigma n square. This is sigma n to the power 4. So I have n over sigma n square as this. Okay. So from this step to this step, now I have independent Gaussian random variables with mean sigma n square. So since they are independent, their variances, summation of their variances, okay, basic skills, then there is cancellation. We have this. So what do we see? We are almost done with Kramer-Rao bound calculation. So Kramer-Rao bound is then 1 over this result, this expectation. Okay, I don't want to write it again. So then this is equal to sigma n square over n. So this is supposed to be a function of c, but this is just constant. Where Kramer-Rao bound is, as you see, it may depend on this desired unknown variable. Okay, c. So comparing MSE of sample mean estimator, which is sigma n square over n, and Kramer-Rao bound of the problem, we conclude that sample mean is an efficient estimator. So this is very good news, because sample mean satisfies all of these properties. So efficient estimator means that is the end. I don't need to look for any other estimator, because this is the lower bound for all estimation error, for all estimators, in terms of estimation error variance. So this is the lower bound. So I reach this lower bound by this sample mean estimator. Then that means that there is no other estimator that can beat this. Okay. So it is unbiased, it's consistent and efficient. Okay. So let me write a general comment. So in general, Kramer-Rao bound depends on unknown variable theta. But in this case, it does not depend on theta. So this is not a function of c in this example. And for other problems, there can be several parameters and the joint estimation of several parameters of interest can be an issue. So let me give an example, even though this is just a sketch. So let's say that I have such a case, A, e to the j phi, e to the j omega n, plus noise, okay, or noise vector, okay. So let's say that this is Gaussian vector with zero mean and covariance matrix sigma n square I, okay. So this is a noise vector this time. Since we have studied random vectors, we have no difficulties in understanding this. Well, this can be even complex Gaussian, but I mean, let's do not get into so much details. Okay, so what else? Now, over here, A, phi, omega, amplitude, phase, frequency of complex exponential. So this is the signal of complex exponential. Are parameters of interest. Can be parameters of interest, okay? So you don't know the amplitude, you don't know the phase, you don't know the frequency of this complex exponential. Then you come up with, maybe you use FFT, okay? You take the Fourier transform of R vector and you are looking for the peak value and so on. Maybe you have an estimator like that in your mind, okay? Now you define an SNR. Well, let's say that SNR is, I'm just making this up for this example. This is like A square over sigma n square, okay? So these are all real quantities, as you see. So I'm trying to estimate them, and my y-axis is, let's say, variance of omega true, whatever it is, minus omega true, let me write it over here, variance of true value of the frequency minus its estimate given this R vector. Okay, it's a function of this. Maybe you are taking this, you know, FFT of R, looking at the peak value in the magnitude spectrum, and the peak location, you declare it as frequency. Okay, you do something like that. Now the issue is this. Now, so this black curve is Kramer-Rao bound. Okay. So you may have a performance like this. So this is your estimator. Something like this. So this is estimator 1, error variance. You may have another estimator. So this is maybe something like this. So this is estimator 2, error variance. Or let me write MSC, because let's say we have something like that, MSC. Okay, so Kramer-Rao bound is this. So what we see is that at high SNR in this, both of these estimators are, this is the SNR axis. At high SNR, these estimators are, let's say, meeting this Kramer-Rao bound, okay? So they converge on this Kramer-Rao bound value. So as you see that these estimators cannot produce a better estimator, a better error variance than this Kramer-Rao bound, okay? There are some issues about the unbiasedness and so on, but okay. Then we say that if an estimator, let's say, meets Kramer-Rao bound at high SNR, or for large number of large number of observations, meaning that n goes to infinity, and high SNR means SNR goes to infinity. So I should define some SNR. Then such an estimator is called an asymptotically efficient estimator. Okay, so this is a definition. As you see that as SNR increases, suddenly some of these estimators are converging. Suddenly means in a narrow range of SNR. They converge to this Kramer-Rao bound. Okay, so those estimators converging to this Kramer-Rao bound, they are called asymptotically efficient estimators. So sample mean is not like that. Sample mean is always on the Kramer-Rao bound. It's always efficient for all C values and so on. But some of these estimators, like this frequency in the frequency estimation problem, estimation of this omega, we see such a behavior. Okay, and you can see that from the signal processing viewpoint. So if I have such a case, if I can increase by doing some signal processing, if I can increase my SNR from this, let's say delta SNR, from this point to this point, let's say for the red curve. So red curve is behaving very poorly in comparison to Kramer-Rao bound, lower bound. Okay, but if I can manage to increase my SNR this much, SNR increase, you can see that it's almost like on the Kramer-Rao bound. So this is a signal processing task, increasing the SNR such that this estimator will be performing better. So what can you do to increase the SNR or decrease the noise, whatever you do? Okay, that becomes an issue. Okay, so that's our final definition, asymptotically efficient estimator. Let me write what's called a Folk theorem. This is not a provable theorem, but it generally holds true. Maximum likelihood estimate is an asymptotically. Of course, there are some counter examples, but for many problems, asymptotically unbiased and efficient estimator. So this is the reason that we use maximum likelihood estimation, efficient estimator, because at least we know that it is under these conditions, high SNR or large number of observations, it's asymptotically unbiased, and it is the best estimator that we can get in this high SNR regime. Okay, so this is a Folk's theorem. There is no proof for this, but in general, in many applications, this holds true, and this is the reason that we are using maximum likelihood. Okay, so we will continue with more discussions.